Greetings of the day, dear students. In this video, we are going to discuss about the three-phase transformer, and we will see its advantages, what are the drawbacks, what are the different modes of connection of the primary and secondary, and also we will see how to represent its connection, if it is in a star connected manner or delta connected manner, and also we will discuss one example on this topic, right? Please observe, dear students, with respect to the three-phase transformer, generally the power is generated at the three-phase, and the power is to be transmitted for long distances at higher voltages. Why? Because if the voltage for the same amount of power to be transferred, if the voltage levels are high, the current magnitude will be low. Once the current magnitude is low, obviously the amount of current flowing through the lines will be less, right? And those current has to be traveled for the long distances. Because of that, I square R losses will be low. So for that sake, practically what happens is, from generating stations, the power is to be transmitted, right, at higher voltage levels. Once it is transmitted over long distances with higher voltage levels, at the receiving end, again the voltage levels will be brought down to the lower voltage levels, right? Most of the times the voltage levels will be of 66 kV, 110 kV, 132 kV, or 220 kV and 400 kV. These are the standard voltage levels, right? So with the help of these three-phase transformers, we can transfer the power for long distances at higher voltage levels, right? Now, coming to the advantage, for example, these three-phase transformers will be of very considerably less weight, and also they will occupy less floor space, and also the cost will be less than if it is compared with the three individual single phase transformers of equal rating. For example, if you want to transfer the some 100 kVA power with the help of three phase transformer, and also the same 100 kVA power with the help of some three individual single phase transformers, then it is better to prefer single transformer of three phase. Why? Because compared to all the three individual single phase transformers, the overall weight of the three phase transformer will be less, and the place occupied will be less, the cost also will be less, right? And these are all the main advantages. But what is the disadvantage? For example, if you are using one unit of three phase transformer, if any one of the phase becomes defective, the whole transformer is to be replaced. That is the drawback. If any one of the phase gets disturbed, the whole transformer is to be replaced, right? And of course, the transformer can be of either, as discussed earlier, it can be of either core type or shell type. And one more very important point, once we have opted for the three-phase transformer, right, its primary and secondary connections can be of either a star connected manner or delta connected manner. How do you understand that? Based upon the star and delta connection, for different combinations are possible. For example, the primary can be star and the secondary can also be connected in a star manner. Similarly, the primary can be connected in star manner and the secondary can be connected in a delta manner. And also primary connected in delta and secondary also in delta. Secondary is also connected in delta, and the primary in delta and the secondary in star. Like this, it can be of either star connected or star delta connected or delta delta connected or delta star connected. So four different combinations are possible depending upon the type of the connection given, right? So let me consider one example. For example, this is the cross-sectional view of a three-phase transformer. and this red lines indicates the high voltage winding, and this blue lines or black lines indicates the LV winding, like this. Here three phases: phase A, phase B, phase C, or phase R, Y, B. Three phases are there. And on nameplate details we can observe, if you have used capital letters A1 and A2, it represents it is with respect to the primary winding. Similarly, B1, B2, C1, C2, capital letters we have used for with respect to the primary winding. Small letters A1, A2, B1, B2, C1, C2, with respect to the small letters we will use small letters with respect to the secondary winding of three phases. Secondary winding of three phases, right? So this is a cross sectional view of a three phase transformer. Now let me discuss about the voltage and current relationships between the line values and phase values of a three phase transformer if it is connected in different manner. For example, if the primary is connected in star manner and the secondary is connected in delta manner, primary is connected in star manner, secondary in delta manner. Dear students, very one important point is, if nothing is specified, somewhere if you have seen some 200 by 400 volts, if nothing is specified, this 200 and 400 represents the line values. Which value? Line value. Those are not the phase values or instantaneous values or some other values. Those represents the line to line RMS values. This 400 represents the V between, it is the line to line RMS value. This point is important, right? Now in this star manner, if you observe, all the three windings are connected at a common point, neutral point. This is phase A1, A2, B1, B2, and C1, C2. It is connected in the star manner, the primary winding. Now the voltage between any two lines is considered as V. This is the line voltage. This represents the line voltage, right? Now the voltage between the line and the neutral, this is the phase voltage. This is the phase voltage. And for star connection, from DC circuit basics we have seen the phase voltage is equals to the VL by root 3. Line voltage divided by root 3 will be the magnitude. For example, if somewhere we have seen the line voltage is 400 volts, so obviously the phase voltage, the single phase voltage will be how much? 400 by root 3. So it will be around 400 divided by root 3, we will get 230.9 volts represents the phase value. 230.9 volts represents the phase value if the line value is 400 volts. For the given voltage values, if nothing is specified, by default they are to be considered as line values, line to line RMS values, right? Yeah. Now in this star connection, of course, in the star connection, the line currents will be same as phase current. For example, the line current will be same as phase current. Whatever current is flowing in the line, that is the same current is flowing in the phase A also. So for a star connection, line current is same as phase connection, phase current, line current is same as phase current, but the phase voltage will be equal to the line voltage by root 3. That is what we have written here. V phase equals to VL by root 3 and I phase is same as IL. But whereas in delta connection, whatever the voltage that is existing between two lines, okay, if this is the line to line voltage, the same voltage is existing across the phase A. So obviously our phase voltage is same as line voltage if it is delta connected. Very important. Phase voltage is same as line voltage if it is delta connected. Similarly, if you observe whatever the current is flowing in this, for example, in this line, but the current that is flowing in this phase, the phase current and line current, the phase current will be IL by root 3. The phase current will be IL by root 3. This is important. So dear students, simply to say, in star connection, in a star connected three phase transformer, the primary is star connected, V phase equals to VL by root 3, I phase equals to IL. in delta connected manner. If the windings are delta connected manner, three phase windings are connected in delta manner, then V phase equals to VL and I phase equals to IL by root 3, right? Now what about power? Either these two formulas are okay, active power or real power expressed in watts. Most of the times, for example, somewhere if you have seen root 3 Vi cos phi or some 3 times Vi cos phi, both are totally. But the moment you have used root 3, then obviously this voltage and current values must be line values, very very important. But if you have used 3 Vi cos phi, then this voltage and current values must be phase values. That is as simple as that. Very very important. So dear students, if you are using root 3, keep in mind, very very important, the voltage and current values are line values. If you are using 3 times Vi cos phi, then this voltage and current must be phase values. 3 times V phase I phase cos phi or root 3 VLIL cos phi. Both the things are correct only, right? Yeah. Now obviously these voltages, these phase voltages or currents, this each phase will be at 120 degrees apart from each other. These are the basics from AC circuit basics. You can observe from phasor representations, all those things, and these phase voltages will be 120 degrees apart from each other. If it is a balanced system, magnitude wise will be same, and the angle differences will be, if it is here, this angle will be 120 degrees, and again with respect to this one, the 120 each phase will be 120 degrees apart from each other. If the system is balanced source, magnitudes of the voltage must be same and the angle must differ by 120. If it is three phase balanced load, both magnitude and angle must be same, right? Yeah. Now if it is at any instant, if it is a perfectly balanced, right, the vector sum of IR by IB will give you 0. If it is unbalanced, some amount of current will flow through the neutral wire. In a star connected manner, if the system is perfectly balanced, no current flows through the neutral wire. If it is unbalanced, okay, this IR plus IY plus IBB will not be equals to 0. That much amount of magnitude of current will be flowing through the neutral wire, right? So that is the reason why the system is to be, in order to avoid huge amount of current flowing through the neutral wire, the systems are to be always taken care to maintain at the balanced condition. All the three phases are to be equally loaded. Utmost care is to be taken to maintain the system under balanced condition. If it is unbalanced, some the current will be flowing through the neutral wire, right? Now let me discuss a small example. A three phase 50H transformer has delta connected primary and star connected secondary. The line voltage being 22,000 volts and 400 volts respectively. The secondary has star connected balanced load at 0.8 power factor lagging. The primary line current is 5 amps. Determine the current in each coil of primary and in secondary line. What is the output of transformer in kilowatt? What is the output of transformer in kilowatt? Dear students, wherever the problems are coming, I am repeating the same points in all my videos. Please kindly represent the given data with the proper variable names. Once you represent the given data with proper variable names, 50% most of the problem is solved, right? Yeah. Now observe, dear students, the primary is delta connected, secondary is star connected. It is a three phase transformer. The operating frequency is 50 Hz. The primary line voltage, of course he has specified here. If even though he has not specified, this voltage is to be considered as line value only, line to line RMS value, right? Now the primary line voltage is 22,000 volt. The secondary line voltage, secondary V2 line voltage L, V2L, secondary line voltage 400 volts. Power factor cos phi 0.8. This cos phi is given 0.8 lag. The primary line current, the primary I1 line current I1L equals to 5 amps. Now he is asking what could be the primary side phase current, secondary side line current, and also the power. The power, output power is how much? Output power is how much? This is what we are going to focus now, right? So clear up to here? Yeah. Now dear students, let me draw in the form of a diagram from the data given. He has specified us the primary is delta connected. So we have connected one end of the winding, second end is connected to the first end, and the second end is connected to the first end. Here again like this, it will go like this is connected in delta manner primary, and he has specified the current drawn is 5 amps, primary current drawn by the transformer, and he has specified between two lines, as it is a delta connected manner, 22,000 volts. But in delta connected manner, what happens, line value will be same as phase value. So obviously the phase voltage V1 phase or I1, 1 for primary, L for line, P for phase. So the primary side line voltage is same as phase voltage because the connection is delta, right? So both the voltages are same, 22,000 volts. Come to here, star. All the 3 points connected at what common point, neutral point. Now this is the current flowing in the secondary, right? Line current I2L. Of course, if it is this is a star. Now whatever current flows in the line is also same as I2 phase. I2L is same as I2 phase. But he has specified between two lines the voltage 100 volt is important. So obviously what will be the phase value between any two, between line and the neutral? Line value by root 3, VL by root 3. So 400 by root 3 will be our secondary side phase voltage. Therefore, dear students, from this diagram, V phase equals to VL, I phase equals to IL by root 3 because this is a delta connection. In secondary side, phase voltage equals to line value by root 3 and the phase current is same as line current because this is a star connected manner. Now, depending upon the values, we can substitute. Primary side, phase voltage 22,000 volts. And V2 phase, V2L by root 3, 400 by root 3, that is 230.9 volts. So now we can calculate the ratio K, N2 by N1, V2 by V1. So V2 phase value by V1, primary side phase value, secondary side phase divided by primary side phase. Secondary side phase value is 230.9 and the primary side phase value is 22,000. So the value of K is 0.01049. Similarly, using this ratio, we can calculate the currents. I1P by I2P. Primary side phase current divided by secondary side phase current is equals to the K. Already we know the value of K. Based on that, we can calculate the secondary side phase current. I2P equals to I1P by K. But I1P is how much? Whatever the phase current, because the primary side, in the primary side, the phase value will be line value by root 3, but already line value is given 5 divided by root 3. So this is our I1 phase. Once you substitute this I1 phase, and already you have calculated K value depending upon the voltage ratios. So once you substitute I1P and K, we will get secondary side phase current. It is around 277.5 amps. So this is the secondary side current. Now once we know all the values, the power is given by root 3 VL IL cos phi Overall, you can also take 3 times V phase, I phase, cos phi, right? Based on that, root 3 VL cos phi, root 3 VL line voltage is 400, line current is 270, 277, is it 277? Yeah, 277.5. So you will get around 152.365 kilowatt. This is the power output, 152.365 kilowatt. Clear? So this is what all about the three-phase transformer. In this entire discussion, dear students, the key discussions are, the key points are the that windings can be of different combinations are possible. Either it can be star star, star delta, delta delta, or delta star. But whatever might be, if it is star, phase voltage equals to line voltage by root 3. Phase current is same as line current. If it is delta, phase value equals to the phase voltage equals to the line voltage, and phase current will equal to the line current IL line current by root 3. Phase current will be equals to the line current by root 3. These are the important basics. Power root 3. If you are using root 3, please take care. This voltage and current must be line values. If you are using 3, please take care. This voltage and current must be phase values. That's the only difference. If it is unnamed details, capital A, capital E, capital C for primary winding, small a, small b, small c for secondary winding. This is the cross sectional. The main advantages. If somebody asks you what is the main advantage of a three phase transformer, instead of using 3 individual single phase transformers, if you use one three phase transformer, the weight will be less. The weight will be less. It will occupy less floor space, and the cost also will be less. But what is the drawback? If any one of the phase gets defected, the whole transformer defective, the whole transformer is to be replaced. The whole transformer is to be replaced, right? Why the power is transmitted over high voltages for long distances? Because if the voltage levels are high, for the same amount of power to be transferred, if voltage is high, current will be low. Once the current is low, because it has to travel long lines for 180 kilometers or 120 kilometers, some 80 kilometers, like that, the line is to have some resistance. When the current magnitude is very high, I square or amount of power will be lost in the lines itself. For that sake, what they will do is they will transfer the power at higher voltage levels. Again, while using that power, they will step down the voltage to the lower levels, right? Thank you.